Alright, so in this video we're going to discuss how to actually go about finding eigenvalues and eigenvectors. So in the last video where we ended was we said, okay, if I had an eigenvalue lambda, right? So if lambda is an eigenvalue, turns out that is sort of if and only if this particular determinant vanishes. The determinant of A minus lambda times the identity. Okay, and one of the things you'll find is if you take that determinant, if you expand it all out for a particular value of lambda, you find that what you get is sort of a polynomial in this variable lambda. And you're looking for the zeros of that polynomial. So what you might do is you might say, well, you know what I'm going to do is I'm going to start with, say, x, right? X is some unknown. I'm going to compute this determinant. I'm going to set it equal to 0. And the zeros of that polynomial, those are going to be the eigenvalues that I'm looking for, right? So they're going to be the solutions. So the eigenvalues are going to be the ones such that when I plug in x equals lambda, I get 0, right? You might be concerned, notice that I've done the other order here. This is strictly a matter of preference, and you can try it either way and see which one you like, because this, I could pull out a minus sign here and write it like this. And we know that if you have a scalar multiple inside the determinant, you can pull it out, but it gets raised to the power of however many rows you have. So I would get minus 1 to the n times the determinant of a minus x times the identity. So switching the sign costs you at worst an overall minus sign in this polynomial, and it's strictly a matter of taste as to which way you want to do it. The advantage of doing it the way you see it defined on the screen here is that you're going to get a polynomial. If you multiply everything out, we'll do this example here, you'll find that you get a polynomial that looks like, x to the n plus some lower order stuff, whereas if you do it the other way around, if you do it with the a minus x times the identity, the setup is a little bit easier because all you have to do is you basically just put minus x minus x minus x down the diagonal, and then you do the determinant, right? So you just kind of, all you do is subtract x's down the diagonal, and you work things out, which can be convenient. But you do find that some of the algebra, when you do it that way, kind of can get trickier. So if you're worried that you might make sign errors doing the setup as shown here, then do it the other way around. If you think you're more likely to make an algebra error, then you might want to do it as is. So let me show you how it would work with the definition given. You can try it the other way around. You can decide which one you like better. So what we do here is we say, because the characteristic polynomial is, so it's going to be this 3 by 3 determinant. So I do x times the identity, so that means x is down the diagonal, right? 0 is everywhere else, but then I'm subtracting a, so I subtract off the entries of a. So minus 2, 0, minus 3, 0 minus minus 1 becomes plus 1. 0 minus 0, still a 0. Sorry, that was a bad 0. Let's try that 0 again. 0 minus 2, minus 2. 0 minus 1, minus 2. X minus 0, it's just good old x, right? And now you evaluate this determinant. And I'll give you the bad news now. There's really not much in the way of shortcuts when it comes to doing these determinants. Computing eigenvalues is sort of a notoriously difficult problem. There are no computational shortcuts. There are a lot of very lucrative applications to finding eigenvalues. One example is given by Google's PageRank algorithm. Right? Turns out that Google's whole search engine, that whole search algorithm is built on finding eigenvalues effectively, and so. If you know good ways of finding eigenvalues, you can actually you can make some money off of it. But unfortunately, there's no way to do it other than just a good old cofactor expansion. Let's go down the first column. Okay, so first entry is x minus 2. If I delete if I delete row 1, column 1, I'm left with x minus 2 minus 2x, right? 0 in the middle, and then I've got minus 1. Again, my signs down this first column go plus, minus, plus. So I've got plus signs for both of them. And if I delete column 1 and row 3, I'm left with minus 3, 1, x, and minus 2. Oh, we're missing something. How did that escape? Minus 3, right? I got to subtract off a. There's a 3 in that spot, so that should be x minus 3. Let me make sure that's fixed. X minus 3, x minus 3. Okay, there we go. So now we expand these 2 by 2 determinants. So we've got x minus 2 times, so what do we get here? X squared minus 3x minus 4, subtract. So what do we have here? Minus 3 times minus 2, that's 6. And then I subtract off x minus 3. Right? And now from here, we could, if we really wanted to, we could expand this out. I'm not sure that we really want to. Well, okay, let's do it. Let me just work out what this is. So this is going to be 6. Push that minus sign through here. This is going to become plus x minus 9, right? And so let's say we wanted to kind of expand everything down. If we did it, there's an x cubed term. What are the x squared terms? Minus 3x squared minus 2 more, minus 5x squared. What about the x terms? There's a minus 4x plus 6. That's 2x plus 1 more, 3x. And then minus 8, or sorry, plus 8 minus 9 minus 1, right? So you get your characteristic polynomial. But from there, you still have the problem of finding the zeros. And for this particular one, I can tell you right now that there aren't any nice ones, okay? The only possible rational roots for this guy are going to be plus 1 and minus 1, and we can check that if we tried x equals 1, we would get 1. Minus 5, we don't get 0. If we try minus 1, maybe minus 1 works. Minus 1, minus 3, minus 1. Nope, neither one of them works. So there aren't any rational roots, so you'd be looking for irrational roots, maybe even complex roots. So factoring can be a big problem, obviously, when it comes to finding these, right? So you make it sound simple. Oh, yeah, you calculate this characteristic polynomial, you find the zeros, but finding zeros of polynomials, it's not that easy. So to make our lives simple, let's stick to a 2 by 2 example. Okay, so let's find the eigenvalues and the eigenvectors. So the first thing we're going to do is we're going to find the eigenvalues. So let's see. We did x times the identity minus a last time. Let's do it the other way around this time so you can compare, see which one you like better. Okay, so we have 1, so subtract x's down the diagonal, so minus 5, 1 minus x. Okay, so we multiply everything out, so we get 1 minus x squared, subtract, so minus 5 times, so minus 25. All right. Here's probably one place where I think some people might like it the other way around, is just because somehow doing x minus 1 squared is easier than doing 1 minus x squared. But nonetheless, we can work that out. X squared minus 2x plus 1, so we get minus 24. Okay, so that guy is going to factor. That's going to factor as x minus 6 times x plus 4. Okay. And so then we say, all right, so when is this thing going to be equal to 0? It's going to be equal to 0 for lambda equals 6 and lambda equals minus 4, right? Because 6 minus 6 would give me 0, minus 4 plus 4 would give me 0. Those are the two possible zeros. And by the way, one of the things you can see here is that you can never have more than 2 eigenvalues for a 2 by 2 matrix, because whenever you compute this polynomial, right, so the eigenvalues have to be zeros of the polynomial, and it's always going to be a quadratic polynomial for a 2 by 2 matrix. And a quadratic polynomial never has more than 2 roots. So you've got your eigenvalues, so now what about the eigenvectors? So for the eigenvectors, well, remember what the eigenvectors are. They're solutions to this homogeneous system of equations. A minus lambda times the identity all multiplied by x equals 0. So you solve this system for each eigenvalue that you have. So let's see. So if lambda equals 6, we'd say so a minus 6 times the identity is going to be minus 5 minus, so I subtract 6's down the diagonal, and there's what I get. Remember that these values of lambda are the ones that make a minus lambda times the identity not have an inverse, so we expect to see 2 rows that are multiples of each other. In this case, the 2 rows are the same, and so if we take this guy and we send it down to reduced row echelon form, you get 1, 1, 0, 0. And so we're looking for a solution, and so we say, okay, so imagine now, imagine that you're kind of doing the augmented matrix, so a minus 6i, and then we put our zeros over here, so then we add on our row of zeros. You know, you don't need to put the row of zeros on. You can probably kind of see how this should work, right? So if our x looks like, maybe call this thing x1, if it looks like a b, we can see that b is free. A plus b equals 0, so a equals minus b, right? So this looks like minus b, b. So it's b times minus 1, 1. So what we do is we say, you know, I can take b to be any number I want. So any scalar multiple of an eigenvector will do. So you choose the basic eigenvector. You set your free variable equal to 1, and you take the vector that's left. So setting b equal to 1 gives me, so for lambda equals 6, so we'll call that lambda 1. I get x1 equal to minus 1, 1. And feel free to check that if I take my vector and I multiply by my matrix, I do indeed get 6 times x1. So a times x1 is equal to 6 times x1. All right, so I'll give that as an exercise for you to check. ax1 equals, remember that's the whole point, is that it has to satisfy this equation, so you should probably check that at the end and make sure that it works. Okay, and then you can do the same thing for minus 4. So a minus 4, so a plus 4 times the identity is 5 minus 5 minus 5, 5. And this time, if you send that guy to reduced row echelon form, you're going to get 1 minus 1, 0, 0. And you can quickly work out that in this case, if we do, maybe call this guy x2, right? It's got to be, so if you kind of go through all the steps, you find that it's got to be some scalar multiple of the vector 1, 1. And again, you can set t to be anything that you want, so you set t equal to, let's say, 1, and you get that your second eigenvalue is minus 4 with the corresponding eigenvector of 1, 1. And again, you can check that if I do a times x2, I do get minus 4 x2 as expected. Okay, so there's our eigenvalues and our eigenvectors. All right, one more example. 3 by 3, but it's not such a bad 3 by 3 example because we've got a couple of zeros in the matrix. This is going to help us out. Okay, so we're gonna do first the characteristic polynomial. Okay, so let me do it the other way around. So let me do, again, let's do x times the identity minus a. So that's going to be x minus 3, 0, 0, minus 1, x minus 1, 1, minus 5, minus 1, x minus 3, right? So notice you got to remember to change all the signs around when you do that. This is the disadvantage of doing it this way, okay? So I'm going to expand along the first row. I get x minus 3 times that guy. So what do I get? I get x minus 3 times, so x minus 1, x minus 3, minus minus 1, so plus 1. Right? But I've got to sort of factor this other quadratic, so I've got to expand and simplify. So I've got x squared minus 4x plus 3 plus 1 more, that's 4. So what I get, and this is, so what I get is x minus 3 times x minus 2. That's x minus 2 squared. So I get two eigenvalues, right? I get two eigenvalues. I get lambda 1 equals, let's put them in increasing order. So I get lambda 1 equals 2, but notice that that one shows up twice. It's a repeated eigenvalue. And lambda 2 equals 3. When an eigenvalue shows up more than once, when you get a repeated root in your polynomial, this makes things more interesting, because it turns out that when you have a repeated root, sometimes you only get one eigenvector that comes along with that eigenvalue. Sometimes you get two. Okay. So I'm gonna let's see, how are we doing for time here? We've got we're at 17 minutes, so I think we're gonna put this to a stop. We're gonna let you guys see if you can find the eigenvalues on your own for an exercise, and see what happens with that second one. See if you get one or do you get two.